I wouldn't say if you know, you know. I ask kind of the odd things out of those lists. If you don't read them, oh, why aren't the knuckle pin holes equidistant? To compensate for the elliptical path of the articulating rods. Those elliptical paths or oval paths. Let's make sure I don't get people. I think the word that they use is ellip equals oval. There we go. The elliptical or oval path of the articulating rods. Okay, so you need to read them. If you don't read them, you will get questions wrong. I'm almost certain of it because I picked some weird things and they stood out to me as, oh, hey, that's kind of cool. The only one that I do give you, you're not going to operate, or you haven't actually operated that drill press and changed speeds on it. I can't remember if I got the question out of the test or not, but it might still be lurking in the bank. If it asks you, how do you change speeds on the International Model 75-010 drill press, you do it with the motor running, which is weird. Don't turn it off. You do it with the motor running. And in normal times, that is a fair question to ask because you will have done it and you'll know that it does not allow you to change speeds with it off. There's a little dial and you need to adjust it with it running. So, no, just read the safety part. Just read the safety part. That was the only one where I went a little bit deeper because you actually used the tool and you should know how to turn it on. Well, no. Woodchop isn't a lie. If it's a belt drive with a belt that you pick up and put on a different pulley, you do stop it. But that particular model has got an electronic control. So, and I wanted students to actually think about what they had done. So it varies by equipment. So, okay. What are some materials that non-sparking tools can be made from? Folks, what are some materials that non-sparking tools can be made from? I'm looking down here, a couple of lines. Brass, bronze, basically stuff with copper in it, which makes them super expensive and pretty heavy because copper is really expensive. Okay, what do you got to watch on your non-sparking tools? That they don't get dirty and get some steel in them, right? Because if you beat away on a steel bolt long enough, you might chip a piece of steel off into it. Now it's not non-sparking anymore. Why do I teach you about non-sparking tools? Because Transport Canada tells me to. That's the only reason. I don't use non-sparking tools when I'm working on an engine. How ridiculous. But they want me to teach you why I do, and I'm telling you that I don't. But I teach you a little bit about them. Okay, safety precautions on compressed gases. Big deal. If you spray it at your skin, you can give yourself a blood embolism, which is basically a bubble of air in your bloodstream, and then give yourself a stroke. So that's the biggest thing. You could also blow something into your eye, and it's noisy. Okay, 4 fire classifications, A, B, C, and D. We already talked about that, right? Anybody need a review of A, B, C, and D? Happened to your teacher, one of those things did. Yeah. Which? The stroke, the blew it into his eye, or hurt his ears? Hurt his eye, yeah. That's, oh, a stroke. Nasty. That's scary. All right, history. Who built the first model helicopters and what was the power source used? Ding, ding, ding. This was our source of steam. Right. And which aircraft used steam as a power source? That was the balloon. Right. Balloon. Which aircraft were the first to fly using internal combustion engines? Yeah, the first were actually some models, right? And then the Wright brothers had the first one that was carrying people. When did they accomplish this feat? We already covered that. Why do gas turbine engines, 1903. Why do gas turbine engines largely replace piston engines? Why are almost all modern aircraft using gas turbines instead of piston engines? They are not more efficient. They are less weight, power to weight. If you pick up a 250 horsepower, a 300 horsepower gasoline piston engine, that's what you're working on right now. Could any of you pick up that engine by yourself? Because I can't. Bugger's heavy. Yeah, easy deadlift, sure. If you go downstairs and pick up a 250 horsepower Allison 250 engine, I mean, probably one person could pick it up. A 600 horsepower PT6, Pratt & Whitney PT6, is an easy two-person lift. And that's a 600 horsepower engine. They are so much lighter. Why didn't we start using them earlier? We were dumb. Okay, they're really simple. They are very, very simple. It's basically a tube with a fan in it. Like, I want to teach level 5 one of these years because they're so simple. It's a tube with a fan in it. The hard part is building a fan that can spin at 40,000 RPM and 3,800 degrees. That's the hard part, right? Getting a fan that'll do, well, we've got a turbine inlet temperature of 700 degrees Celsius at, 10,000 RPM on the Convert 580 uses a turbo shaft engine, turboprop engine, and I recall from my numbers that 783 degrees Celsius is the maximum turbine inlet temperature, and it's spinning at tens of thousands of RPM. That's just hard to, the metallurgy is difficult, but the engines are very, very simple, in concept at least. Okay. So what types, now when did this happen? When did this happen? When did the gas turbines take over? Give me a decade. 1930, 1940, 1950, 1960. All right, 1920s. What was flying around in the 1920s? Here's how I tie it. The World Wars. 1910. 1903, first airplanes at all, right? 1913, World War I. 1939, World War II. What was flying around in World War II? Did we have gas turbines in 1942 or 1939? No, by the end of the war, by 1944, Hitler had a couple. And the reason that they didn't win the war for him is the Allies had bombed out his fuel supply, and they were all sitting there out of gas on the ground, and it's really easy to shoot an airplane on the ground. So that was their trick. The Luftwaffe had a very, very deadly high-performance aircraft, but they didn't have any jet fuel. So they lost the war because of that. So the golden age for piston engines is generally considered to be like the 1950s. And then we moved into gas turbines. That's Cap. Are you saying I'm lying? Sean was capping. What's Sean capping? Nope. They only made 2. Oh yeah, they made more than 2. Yeah, they made way more than 2, but they didn't make enough jet fuel. Yeah, they had a problem with that. Okay. So what type of modern airplanes still use piston engines? Modern aircraft that are still using relatively low altitude, relatively slow speeds, and small. So small, low altitude, low speed. Yeah, Cessnas, Pipers, Moonies. Um, relatively slow, like under 200 miles an hour, relatively low altitude. I mean, you can build a high altitude, uh, you know, relatively high speed piston engine airplane, but we just don't bother. We move to gas turbines. Okay, pros and cons. Radial engine. What's the advantage of a radial engine? What's the biggest advantage of a radial engine? Power to weight. Yeah, compared to other piston engines, excellent power to weight. What's the biggest disadvantage? Torque effect? Oh, you're thinking of the rotary radials. The rotary radials had a hell of a problem with torque effect. Rotary radials are dead. I don't teach about them. The static radials don't have much of a problem with gyroscopic effect because they just spin the propeller shaft, which makes way more sense. Power to weight was their advantage. What's their disadvantage? Size? They kind of died because they hit. There's not many out there because they hit a weird spot. They make like 6, 8, 900, 1,000 horsepower, and at that point we moved to gas turbines. But Braden, you've nailed it. They've got all of the aerodynamics of a pie plate flying the wrong way, right? They take a frisbee and push it the other way. That's a radial engine, right? Terrible streamlining. So that's their big disadvantage. Okay, what about inline engines? What's the advantage of inline engines? Compared to a radial engine, excellent streamlining. What's the disadvantage? Bad cooling and terrible power to weight. Have you guys had the chance to pick up the crankshaft in our shop? Okay. Uh, I want you to go and pick up the crankshaft for our 6-cylinder opposed engine. I mean, I can barely lift the thing. It's heavy. If you wanted an inline six, it's going to be twice as long, be massive. So the weight of them is just no good. All right, advantages and disadvantages of V engines. They're kind of a blend between the inline and the radial. They're pretty good power to weight ratio. The reason the V engines don't live today is, again, they tended to be 600 to 1,000 horsepower engines, and we just don't need a 600 to 1,000 horsepower piston engine. If you're buying an 800 horsepower engine, you're going to go gas turbine. They were used on a few fighter aircraft in days gone by, and then they just stopped needing much use. Okay, opposed engines are winners in modern aviation. What's the advantage of an opposed engine? Relatively good power to weight, relatively good streamlining, especially on a wing with a twin engine airplane. Nice smooth operation. Disadvantage, not as good of a power to weight as a radial, but overall they've got more advantages than disadvantages. When were V-type engines popular? I already mentioned that. That's the disadvantage for a V engine. Not quite as good streamlining as the opposed on the uh, um, on the wings. They don't lend themselves to air cooling as well. The V engines that were built were all liquid cooled engines, so they're a little bit more complicated. But mostly, if you think back, the Rolls-Royce Merlin V12 and variants of it is really what was developed for aviation, and it's 1,000 to 2,000 horsepower, and it just has no market. And nobody needs 1,000 horsepower piston engine for their airplane. If they want 1,000 horsepower, they want a gas turbine. Yeah, it'd be a hell of an engine in a car. All right. Physics. What type of energy is contained in a spinning propeller? Kinetic. What type of energy is contained in gasoline? Chemical. How is work defined in physics and engineering? Joules or foot-pounds? Yeah, joules or foot-pounds. How do you calculate it? Multiply force times distance, right? Okay. What term describes how fast work is done? Power, horsepower, kilowatts, power. We want more power because we want to go fast. We want to climb fast. How do you calculate power? Work divided by time. Exactly. Okay, and the question that so many people got wrong on the Kahoot, which you might want to get right tomorrow. What is the difference between brake horsepower and friction horsepower? Brake plus friction equals indicated, right? So which one is the one that you're going to always get reported? Brake horsepower, right? And friction horsepower is not just idle, but if I'm idling at 700 RPM and I've got a friction horsepower of 10, if I spin this engine up to 3 times as fast at 2100 RPM, it's probably going to have 30 horsepower of friction horsepower. Does that make sense, Nathan? If I'm spinning the engine faster, my friction horsepower will actually be higher. Yeah, and it's always waste. And the friction rubs things around, turns into heat, and then we got to blow it off in the cooling system. So which one do we desire to be as high as possible? Brake horsepower. Which do we desire to be as low as possible? Friction horsepower. Does that answer your question, Sukran? I think so. Okay. How is twisting force measured? Torque. And how do we calculate it? Force times the arm, right? Distance, yes, but make sure you recognize that it's the arm. Okay, how do you calculate horsepower from torque and RPM, folks? Force times RPM divided by some constant, and we're not worried about that constant right now. And if they're putting out different torques and RPMs, how do you compare them? Multiply them and compare. Right, there are test questions that ask you to do that. It's simple. Multiply the torque times the RPM and see which gives you a bigger number. That's going to do it. All right, moving along in the wonderful world of physics. Wasn't this a fascinating video? That was so well done, hey? Each test, I believe, has 40 questions, roughly. Well, I've got 16 pages of material here. Pages. I'm hoping this isn't, I'm not trying to drown you folks. It's just all the stuff we got to cover. All right, what happens to, I think we're already in the water. All right. The questions are multiple choice, yes. Questions are multiple choice. Well, I hope you aren't feeling too overwhelmed. How'd you do in Mr. In level 1? I mean, weren't his tests pretty similar? They were shorter. They were shorter, but you had more of them. The same amount of tests, but they were shorter. Huh. That surprises me. One each week. Yeah, they asked me to set these up every second week because they were so short of test center time because we got all these students coming in there. I will tell you folks, in general, I haven't seen a remarkable change in the pass fail rate between pre-COVID and now. And one of the differences, this is such a good study guide. I'm being more direct, more helpful with this. So, I'm guiding you straight to the questions. And I said it many times, and I'll keep on saying it. Study these 14 pages, and you'll do well. All right. Okay. What happens to the air density as altitude increases? Decreases. Correct. How does this affect the engine's ability to produce power? It lowers it. Imagine if we took our engine to 100,000 feet, it won't even run. Okay, and how does it facing it forward? Moves more power. We're jamming more air into the engine. When you're flying at 200 miles an hour, there is some compressive effect there. Okay, boiling and freezing point of water in all three scales. All right, boiling and freezing in Celsius. 0 and 100, right? Oh, how does facing the air intake into the wind help the engine produce more power? Oh, well, pretty straightforward. Let's just skim down here. I've got a blank one here. There is my engine intake off to my carburetor and cylinders. Cylinders. Air is rushing here. My airplane is flying forward very fast. I'm going to jam air into here because I'm going at 250 miles per hour. It's windy. Yeah, increase the density if I put my air. Whereas if I, instead of doing it this way, if I faced my air intake this way, how much air would I get in? See that, interviewer? The air was, yeah, okay. That's all it's asking, basically. Okay. Boiling and freezing, 0 and 100. What is it in Fahrenheit? 32 to 12. And what about Kelvin? 273 and 373. So 273. So the Kelvin scale is closely related to the Celsius scale. We just moved to 0. Absolute 0 in all three scales. 0 in Kelvin, minus 273 in Celsius, and something like minus 460 in Fahrenheit. Okay, do we need to go through another example of my doubling and going to half? We lost so many numbers. Just take a look at It's this scale here. I'm just flashing through this scale here. Okay, and like I said, ignore this one. Get rid of that. We don't care about this. Rankine does not matter. Okay, so freezing point of water in Celsius, 0 degrees. Boiling point of water, 100 degrees. You know this. You've known it for 20 years, right? 15 years. That's not hard. Anybody confused on Celsius? No, of course not. Kelvin. Kelvin, they said, if we get colder and colder and colder, we're going to hit minus 273. Physicists like Kelvin because the gas laws pay attention to Kelvin. That's why I teach it. Why do I teach Kelvin? Because the gas laws care about Kelvin. So if I say I want to do half of this temperature, referencing absolute zero, half of that temperature, let's move to a different color, let's go to green, half of this temperature would be right there. Because in physics, the temperatures are all the same. And this one here is the important one to use. So half of this temperature is right there. What is that in Celsius? Well, this looks like minus, 80. So that's what you're going to run into. Minus 136.5. Yeah, it could be. Room temperature Fahrenheit, about 70 degrees. Let me erase some stuff here. That does not matter. You should know it, but I don't think there's nothing on the test. The only reason that room temperature matters, what is the ICAO standard day temperature in Celsius and in Fahrenheit? Because this matters. 15 degrees Celsius, and how much in Fahrenheit? 59. Is what minus 136.5? Half of zero? Yeah, that looks about right. Josh, you're asking, yeah, half of 0 degrees Celsius would be like minus 136. Yeah, you'll probably get one question like that on the test. It's going to ask you to double or halve a temperature. Okay, so that's why 70 is useful, because 20 degrees Celsius is room temperature, 70 degrees Fahrenheit is room temperature. It's not quite, but it's close to 2 to 1. A degree Fahrenheit is about a half a degree Celsius, 1.8 actually, or so, but or 5/9 or something. But it's close to 2 degrees Fahrenheit for 1 degree Celsius. Okay. Do you folks want me to go through these temperatures a little bit more, or can you see it from the scale on your own? You're good? Ooh, are we going to run into the... this thing's going to shut us down shortly, isn't it? Because we've got a 208, 60, 120. Oh, no, we got 4 hours. I think we got 4 hours in the lecture here. We're still good. Okay, moving along. So half of 0 degrees is halfway of, yeah, exactly. So if you're worried about this test question, sketch this diagram and visually you'll see it. Okay, if you're struggling with the math, don't worry about the math. Draw this diagram and I'm going to give you a hint. Don't worry about the Fahrenheit. Just be able to draw this part. If you can draw that part, you can visually do the questions. Okay? Maybe that will relieve some stress. Okay. What happens to the pressure of a gas if the container it's held in is reduced in volume, if the piston moves up in the cylinder? It increases. And how is the density of a gas related to its temperature if we're in an open system? The higher the temperature, the lower the density, right? Inversely related. Thank you, Gideon. All right, which holds more water? Warm air or cold air? Warm air holds more water, yeah. Below 33,000 feet, how are altitude and temperature related? Exactly, inversely. As we go up, it gets cold. Around 35,000 feet, that stabilizes. And when you get really high, it starts to go the other way. But ICAO standard conditions at sea level, you must memorize these: 15, 59, 29, 92, and yeah, that's it. 14.7 psi. It's another way to describe 29.92 inches of mercury. Yes. What happens to the temperature and pressure of gas if it is compressed? They both go up. What happens if it's allowed to expand, which is what we do in our cylinder? Oops. Sorry, folks. What happens if the gas is allowed to expand? Temperature and pressure both go down. Okay. I'm going to pause here for just 1 sec. I want to take. Sorry about that, folks. Okay, so which gear type is the least expensive to manufacture? Spur gears, right. Which one changes the plane of rotation? Bevel gears. What's the difference between a spur gear and a helical gear? The way the teeth are cut, yeah, the angled and curved teeth, yeah. And those angled teeth make for a quieter, smoother contact, right? And release as well. What's the advantage of the helical cut then? Quieter, smoother, and stronger. What's the disadvantage? Thrust, that induced thrust, and they're expensive. Okay. Which bearing type is best suited for very high loads? A plain bearing, exactly, a plain friction bearing. If I wanted to move into the anti-friction bearing, what's the next best? A needle bearing. Thank you. Needle rollers. All right, what's the disadvantage of those plain bearings? Well, high friction. Which type of rolling element bearing has the lowest friction? Ball bearing. And the disadvantage, of course, is that is going to take the smallest load. All right, radial load and thrust load. You just got to be able to see that picture. Radial load is kind of outward on the wheel, and a thrust load would be what the propeller puts on the bearings. Okay, what type of bearings do we use in the crankshaft of our engines? Plain bearings. What type of loads can a simple ball bearing handle? What's a simple ball bearing best equipped for? A radial load, not an axial. Axial is along the axis. It's a thrust, another name for a low, yeah. A simple ball bearing is not good for a thrust load. Confucius say, let's pull this up. Bearings. Bearings. Slideshow. Actually, let's just go down here. There's a picture. How's that? Yeah, this one's a little confusing. Yeah, whatever way works for you. Thrust, axial, along the axle, propeller thrust, and then radial. I don't have any great tips for it. That's all I got. Okay, so a simple ball bearing is best with a radial load. That make sense? Well, there's deep groove ball bearings, and there's those offset ball bearings. Is what I'm trying to differentiate. Like, take a look. There's a simple ball bearing, or then here's one with a. This one's actually got a pretty deep groove on it. Here's my offset bearing. Here's one. Angular contact ball bearing. See how it's more complicated. And that one's great for a thrust load in one direction. Okay, so a deep groove ball bearing can handle any load you give it, right? I think you should know, I can't remember if there's test questions on it, but you should know the difference between a deep groove and angular contact and a shallow groove, I suppose. I don't have a name for them specifically, but a deep groove ball bearing and an angular contact ball bearing. You should know that. Okay, straight roller bearing. What kind of loads can a straight roller bearing take? Radial only. Radial only. And then a tapered roller bearing will take radial and axial. All right, am I moving too fast? Am I doing okay here? All right. Just about done, folks. Why do we sometimes use propeller reduction gearing engines? Propeller reduction gearing. And it's not common. Most of our engines are just direct drive. Why will we sometimes use propeller reduction gearing? To reduce propeller speed. Actually, it's more like to allow the engine to spin faster. We're going to spin our prop at 2400 RPM. But we don't, how many people drive a car with an engine that doesn't spin faster than 2500 RPM? That's a really slow revolution, right? Like what race motorcycle only spins to 2500 RPM? That's really slow. We'd like to spin our engines at least to 3000 or 3500 RPM, but we can't spin the propeller that fast. So exactly, we're trying to get our engine RPMs up into the power band. Okay, 20-tooth gear turning 80-tooth gear. The way to do this is to draw it. Have a pencil and paper in the room with you. All right? Draw it. Okay. Do we need to go through this math? 20-tooth gear is turning an 80-tooth gear. Okay, so the little gear is turning the big gear. So let's see if we can work this through. Little gear turning big gear. What is our reduction ratio? What's our reduction ratio? 4-to-1. Thank you, 4-to-1. So this will turn 80. The output will turn 20 RPM. Very good. Thank you, Mercan and Vincent and Braden. You got it right. Okay. Which gear ratio will give the lowest output RPM? 5-to-3 or 10-to-1? Ooh, all right. Put them into the same common denominator, and it's going to be tough to make a 5-to-3 go down for you. So that would be a 30-to-3 or a 5-to-3, if you want to do it that way. So a 10-to-1 is going to turn at 1/10 of the input RPM. A 5-to-3, it's getting pretty close to a 1-to-1 ratio there. Does that make sense, Mertcan? Who was it who said? Yeah. Do you see your error, Mertcan? Okay. Look at this last page. This is it. Okay, which is always the drive gear in a worm? The worm is always the drive. What happens if you try and turn the driven? The thing just locks up. Okay. We've talked about the thrust. They generate thrust because you got those angled teeth, and that means you need to build a heavy-duty case for everything, or we can use herringbone. Okay, and the three parts of the planetary gear set, there are three elements. There is the element number 1 is the planets and their spider. Element number 2 is the ring, and element number 3 is the sun. How many of them will be allowed to turn in any gear set? 2. How many of those will be? Well, the carrier is part of the planets. The carrier and the planets are one element. Does that make sense, Mercan? Ready to pull up a picture? Yes, it makes sense, or yes, you'd like to see a picture. I'm seeing people want to see a picture. Okay, let's get a picture. Turns, gas laws. Oh, I don't have it up. Do I need a picture? Sukran, do you need me to pull up a picture? Why do helical gears generate thrust? Let's pull up a... Okay, take a look at this picture here. Here's a helical gear. And when these spin, not only does this generate a twist in the other one, it's going to try and spit it up or down. Do you see that, Braden? It's going to generate a thrust in the up and down direction as opposed to just torque. Can you see that with like this gear here? It's going to move it up and down as opposed to just wanting to spin it because of the angle to the gear teeth. So the advantage is we get this soft entry, soft release, gradual meshing. They're stronger. The disadvantage is you need to support it really well because it's going to try and spit it out. And then just that last planetary gear set, right? And I think I've already talked about that one. Yeah, we've got our three elements here. You can see anytime you see the planet gears, there's always a carrier attached to them. I think it was Mertken's question. The carrier is always attached to the planets, and it becomes here's a carrier attached to the planets there. There's no example you'll find with the planets just kind of floating around free. Okay. That's all I got right now. Maybe I should do some attendance here.